Mathematical induction. First principle of mathematical induction. Let S be the set of integers containing the number A. Suppose that S has the property whenever some integer n greater than or equal to A belongs to S, then the integer n plus 1 also belongs to S. Then S contains every integer greater than or equal to A. As an example, we'll prove that given a straight edge and a compass and a unit length, we can construct a line segment of length square root of n for every positive integer n. So we'll use the theorem with A equals 1. This is true when n is 1. So this is by definition because the unit length is given. 1 belongs to S. Now assume that we can construct a line segment of length square root of n. That is, we're assuming that n belongs to S. Then we use the straight edge and compass to construct a right triangle with a height 1 and base root of n. So this is the base root of n. With straight edge and compass we can construct a perpendicular line at this point and then take the unit length here to get this point. Now these 2 points determine a line segment of length. Apply the Pythagorean theorem. Root of n squared plus 1 squared square root of this is equal to the length of the hypotenuse, and it is just root of n plus 1. So this hypotenuse has length root of n plus 1. So n plus 1 also belongs to S because root of n plus 1 is constructible. This completes the proof by induction. S consists of all integers greater than or equal to 1. The second principle of mathematical induction. Let S be the set of integers containing A. Suppose that S has the property that n belongs to S whenever every integer less than n and greater than or equal to A belongs to S. Then S contains every integer greater than or equal to A. To use this form of the induction, we first show that the element, the statement is true for A, that is A belongs to S. We then assume that the statement is true for all integers that are greater than or equal to A and less than n, and use this assumption to prove that the statement is true for n. We will use this theorem to prove the existence portion of the fundamental theorem of arithmetic. which means that we have to prove that any integer greater than or equal to 2 can be written as a product of primes or is a prime. So let S be the set of integers greater than 1 that are primes or product of primes. Clearly 2 belongs to S because 2 is a prime. Assume that for integer n, for some integer n greater than or equal to 2, S contains all integers k such that 2 is less than or equal to k less than n. To complete the proof, we must show that n belongs to S. If n is a prime, then n belongs to S by definition. Any prime belongs to S. If n is not a prime, then n is factorable as a product of two integers a and b, each of them greater than or equal to 2. So each of them must be then strictly less than n. But any such number, by the assumption, belongs to S. So A must be in S and B must be in S. So they can be written, A and B can be written as product of primes. But then n, because it is a product of A and B, replace here A and B as product of primes, you'll get n as a product of primes. So this means that n belongs to S. The second principle of math induction then guarantees that S is equal to the set of all integers greater than or equal to 2, which means that any such integer can be written as a product of primes. And this is the existence portion of the fundamental theorem of arithmetic.